Sounds good.
All right, take it away.
Okay, so today we have Georgia Chalvatzaki from TU Darmstadt. She's the research group leader of the really freshly formed group there, Intelligent Robotic Systems and Assistants. And I've known Georgia for about like 9 to 10 months now. So just to talk about her, she did her PhD from Athens in Greece, and then she moved to Jan Peter's group for a postdoc, and now she's sort of starting her own group there, and really excited for her to see how this goes. She's also been awarded like the RSS Pioneer. She was a part of the cohort in 2020, and that's how I got to know her. She's like a really fantastic person, and it's been fun working with her on a few initiatives this year. And one special honor that's been bestowed on her is she's been nominated for the AI Newcomer of 2021 by the German Informatics Society. And I guess a part of that decision also hinges on a public vote. So if you're watching this, just go over and vote for Georgia. And again, now with all of that aside, Georgia, it's all you. Take it away.
Thank you very much for inviting me. Thank you for the very nice introduction and for calling people out to vote for me. If you have time, I will post the link later. So let me start here. So as Krishna said, I'm Georgia. I'm now starting my new group in TU Darmstadt after getting granted a pretty big, I would say, AI minuter project funding. So now I will talk to you about my research on robot learning for intelligent assistants. So let me start it with some societal facts. Okay, elderly population is constantly rising. There are predictions that say that the elderly population, which is the people that are aged over 65, will reach 2 billion by 2030. On the other hand, our nursing staff is constantly decreasing. Our everyday life has become even more hectic, and now we are living this unprecedented events of the COVID-19 pandemic, where a lot of us are staying in isolation, a lot of people have to stay in quarantine, and who knows what the future will serve for us. So it is, I think, most important than ever that we have personal assistant robots, and we need to push for this line of research. The vision of personal assistant robots is a long-wished vision and dream in robotics and AI society. And indeed, we have seen human-like robots depicted in movies being able to perceive the world around them, perceive humans being able to learn and execute household tasks and adapt to every human need. But why don't we have such robots yet? Well, in the past, we did not have the hardware and the algorithms, but I think now things are different. Now we have robots with anthropomorphic bodies and increased dexterity. We have computational power to accelerate our algorithmic processes, thanks to the GPUs and the clusters of CPUs. We have fast and accurate sensors, and thanks to the deep learning revolution, we have effective algorithms for perception from static datasets. However, there are still missing components that do not allow robots to leave the structured lab environment and enter our houses, like embodied perception, like learning to plan household tasks, interact with humans, and communicate with them verbally and non-verbally in a seamless way. And among the missing components and technologies, I believe that now is the time to address these challenges of learning and manipulation skills and planning long horizon tasks of combinatorial complexity with the human in the loop as the center of the interaction process. And this is actually my main research focus of enabling embodied AI agents like a mobile manipulator robots, that I think it's the most emblematic example of such an embodied AI agent to leave the labs and be able to serve us as personal assistant robots in our houses. So among all these components that I think that the fundamental pillars that we have to address right away, consider the embodied perception, the safe and fast skill learning of the robots, and finally the adaptive planning, not only for executing manipulation tasks, but also the adaptive and safe planning of interactions with humans. And regarding these pillars, of course, that are not resolved yet, I am going to discuss certain topics that I have tackled during my research all these years. And I think that they touch somehow in these fundamental problems. And I will later on explain to you how I plan to tackle the open research problems and potentially even collaborate with the bigger community into this direction. So the topics that I'm going to touch consider the perception and prediction of human activities, the planning of adaptive interactions given the human related information, the encoding and extraction of features in objects with which the robots should interact, and finally, the accelerated manipulation skill learning. But now let me start with the first topic regarding perception and prediction. And this has been one of the central concepts during my PhD studies in Athens, where I was working on developing algorithms for intelligent assistant robots for the mobility support of elderly people, but also with humanoid robots for interacting with typically developed and autistic children in order to be able to evolve and develop their communication skills. But let me start with the mobility assistant robot. One of the key objectives there was to use the visual, the RGBD information, the laser information in order to extract useful features in order to adapt the behavior of the mobile robot to adapt its control strategy for having this natural support during working. Due to the high uncertainty of the depth information, it was very, very difficult to do any kind of estimation, as you can see from the depth sensors. Back then we were using the Kinect version 2. So I started working with the laser sensors that were way more reliable back then. They still are. So one of the first contributions that I had in my PhD was the introduction of the interacting multiple model probabilistic data association particle filter. And in this interacting multiple model, its state refers to a particular state gait phase during working, and its state refers to both legs while working, and it poses a different motion model. And in particular, its state is represented by a velocity Gaussian mixture model that can alter the transition probability function with which are subsequently the dynamics with which the particles are evolving during the propagation. According to this propagation, later on, we had a full probabilistic observation model that considers the distribution of the laser points around the leg. And most importantly, we are considering the data association between the legs in order to avoid cases of occlusions, for example, while turning or when the carer is working in a close proximity to the user and there were sudden jumps, for example, on the tracking to another person, for example. And most importantly, we are considering a representation over both legs jointly that fuels a maximum a posteriori estimation through the Viterbi algorithm that can predict the next gait phase, that continuously drive the selection of this Markovian model in order to select the next motion model and so on. And this framework, it gave us a very effective algorithm that can track the human user in close proximity to the robot while working together with it, with employing only 150 particles, while also being able to do online gait estimation. And this gait estimation can give you also the opportunity to estimate other parameters for the human pathological working that we have used in subsequent works in order to define controllers for the robot. Moreover, I wanted to identify also the stability of the human. So one of the major issues of humans, elderly people, is the fall events. For this direction, I was inspired by research in biomechanics, and I have worked in particular with motion capture data in order to be able to extract the information regarding the fall risk events while walking. And through this research, I was able to create these labels, as you see here, the safe states and the risk of fall states. To give you an intuition, a human, it's in a risk of fall state whenever its center of mass is center of mass, is let's say approaching this base of support that is defined by the legs. So what I did here is that I used the information that I get from the laser data regarding the gait state and the position of the legs. And I've also leveraged the information from the deep posed estimation that we were using the open pose library, from which I was estimating the center of mass of the human. And these features were then fed into an encoder-decoder LSTM network to do the binary classification of safe or fall stability prediction. Now you may wonder, why didn't I use already the pose of the open pose for the whole body as a feature to train in an end-to-end kind of way my network? But those who have worked with this kind of sensors, you may know that in a very close proximity, their sensing abilities are not very well. So you have too much loss of information from the depth sensor, and also the pose estimation is not so reliable. And this is why we opted for this kind of approach. And compared to baseline approaches, because somebody would say, okay, why don't you use thresholds and a rule-based approach to already estimate such things? It seems like the LSTM encoder-decoder is able to capture these temporal dependencies and the interaction between the center of mass and the legs and be able to estimate the fall risk events. Moreover, we wanted to estimate the multimodal human intention of the human in order to be able to interact effectively with the humans. For this reason, we have created a multimodal intention recognition system that leverages speech recognition, human activity recognition, and the gait analysis system that I presented to you before. I will tell you a bit about these modules. In particular, for the automatic speech recognition, we wanted to be able to communicate with the user when he was expressing some specific commands to the robot, like I want to stand up, I want to sit down, and so on. And we wanted to understand these intents. For this reason, we have used a continuous speech recognition module in several different languages because we're working with people from different countries, and an integrated natural language understanding, which we have trained so that it will be able to understand these intents when they were phrased in many different ways, because you may understand that humans tend to say these commands in many different ways. There is not one clear way that they can express their intent. Moreover, we have used the information from a real sense camera in order to have a 3D pose estimation of the human. And we used this pose estimation from which we extracted some features like the 3D human pose and the joints velocity, which we fed inside an LSTM network in which architecture we have used temporal attention and temporal fusion in order to have an effective activity prediction of the human activity. These particular submodules of the natural language understanding and the human activity recognition were fused inside the multimodal communication module, inside the, let's say, a scoring-based approach that would later on decide which is the intent of the user. And this is particularly important for elderly population because sometimes they are suffering from several diseases, so they are not able, for example, to express verbally their intent very well, or they cannot show with gestures what they want to do. So this fusion sim had the best results. And here you can see a brief example where we have worked with patients in a rehabilitation center, and the robot prompts them to do some rehabilitation exercises. And we can see that even if the estimation of the pose is noisy, our network is able to classify the executed activity and provide feedback to the user about the performance. So how accurate is the execution or not of this action. So regarding this line of research, I would like to address some of the open problems that we still have regarding the prediction of human activity. One of the problems that we can see is that the skeleton-based activity prediction is still very challenging, and indeed many robotic applications consider only the human represented as a point mass. The main issues there is the ambiguity in the pose estimation. There are scaling problems. The 3D registration from the depth to the visual to the RGB stream for the skeleton prediction is not very well defined, and all these have many problems for applying it into robotics. Other issues concern human sensitive data, so we are not able to collect massive data for our research through the robotic interaction because we have the problems, for example, of the recognition of humans through their faces. So one line of research that we are currently working on is the usage of the point cloud data for activity recognition. However, one of the open research problems that we are looking into is how we can quantify the sensorial uncertainty in order to achieve lower prediction errors for human-robot interaction and subsequently for robot control. And now,
I have a quick question, Georgia.
Yes.
So in most of these examples, particularly if your application is oriented towards elderly people,
Yes.
Do you think there's an issue with training data as such? Because let's say if you're predicting motion, if you're forecasting motion of pedestrians on a sidewalk, then it's more likely that there's regular patterns in them. But for elderly, is it that each person has a unique pattern that makes a learning of a generic model kind of infeasible or hard?
Yeah, indeed. For in particular for the gait analysis, indeed I tried to train LSTM networks, for example, for gait analysis, and it was very challenging to be able to collect all this amount of data for the different gait patterns that you can identify. And this is actually true. For all the subjects that I have worked with, their way of working was very different from the one of the normal subjects. Regarding the activity prediction, we have done a large-scale initial data collections with, let's say, normal subjects, or how can I say, younger subjects. And then we also leveraged all possible resources that we had to collect the elderly subject data. But yes, this is an open problem still, because don't consider that even the humans, unless instructed exactly on how to execute the task, that they are not going to execute it differently, the younger ones. So collecting data and being able to generalize over this data with humans is very challenging.
Can I also ask you?
Go Flo.
Yes.
Go Flo.
Okay. So on like earlier, you showed that like some of these methods are implemented as an LSTM for the activity recognition. But on slide 18, you have a lot of these boxes, and I was just wondering, like, how many of these are neural networks, and how do you get this to like any kind of reasonable like frame rate, right? Because you want to have a super low latency from activity to the recognition. To
which slide you said? This one?
Oh, sorry, 18. One further.
No. These are not all neural networks, of course. This is just the high-level system architecture. So yeah, neural networks are basically the human activity recognition and the automatic speech recognition and natural language understanding. And all these modules are, so in terms of inference-based, you have to imagine that each more or less of these modules have like a different computer that we are using to calculate the different algorithms, and then everything is built in rows so that we have this effective communication between the different modules. But in terms of the inference, I would say that the architecture that we are using, it's quite straightforward. So we are more bounded by the frequency of the camera and later on the inference of open pose, for example, in this specific application that throws you, in the best case, you can get like a 15 hertz. So then the inference from the LSTM is quite straightforward then. It doesn't drop the performance. For sure,
Okay.
you cannot reach a real-time 30 hertz performance. That is actually, according to studies, more or less the frequency with which you would like your inference to be on, so that you can have real-time control of the robot.
Yeah, gotcha. Thanks.
Yeah.
I had one little point of clarification. I think maybe I missed it, but for the fall detection, how did you get the labels to train the binary classifier? Like presumably don't make people actually fall.
No, we didn't have, so it's not fall or not fall, it's fall risk. So I used mock-up data, motion capture data from the real patients. So we have real patients wearing the motion capture during the data collections. And I analyzed their biomechanical model. And there are in literature, there are specific thresholds while working that identify whether or not you are like in the risk of fall, let's say, area or not. So this was basically the classification. Now you might say this binary classification is a bit greedy, and I would say that is correct. But on the other hand, I will also talk a bit later about it. If you don't do a bit of greedy selection, then you cannot have a very good signal for doing robot control later on. It's not easy to quantify what is this signal you would need for decision making in the end of the day.
Awesome, thanks.
So should I continue, right? Okay, so I will now go to the planning of the adaptive human-robot interactions. We are still looking into these problems of the human and the mobility assistant. And on top, you will see a problem about handover task between the humanoid robot and the little children when we want to maximize their engagement. And I will describe later on what we have done there. So regarding the human-robot interaction scenario in the mobility assistant, what we wanted to do here is basically to control the robot so that it always keeps a reasonable formation in front of the human while the human is working. And in order to do this, we wanted to leverage all this information that we have from the way the human is working and adapt the velocity and position of the robot with respect to the human. In order to do this, we came up with a model-based reinforcement learning approach for this coupled human-robot navigation scenario. I might want to point out that this kind of problem is different to the usual interactive navigation scenario where the robot has to avoid some humans or like follow a human from behind without caring about the safety of the human or things like this. In this case, we have a joint formation, as you see here. The human and the robot have to be coupled and they have to work together as one agent, let's say. So we have a front-following coupled navigation that we cast as a constraint optimization problem. Our aim is to find the optimal control sequence over a finite time horizon by minimizing a quadratic cost that considers as a goal a relevant robot position and orientation with respect to the human. So basically this kind of formation like this here in the supporting scenario. And our goal is to learn this motion model, the interaction model of the human and the robot so that we can effectively plan the robot actions. So we came up with this architecture that not only plans the robot actions based on a learned interaction model, but we also use a prediction model of the human. So we found out during our research that it's not efficient to use as input the current position of the human and the current position of the robot and then predict the next state of the system. We actually, in order to predict better the actions of the robot, we wanted to cast ahead in time where the human wanted to go. So we had here two neural networks. One network wanted to regress the position of the human. So we took the center of mass of the human and we regressed it ahead in time in order to predict the trajectory of the human. But also we had a a parameter network that was taking as input the parameters of walking that we are extracting through our gait analysis system in order to cast, for example, how the stride length of the human will evolve. And why did we do this? Because in the previous slide that I showed you this formation, we have analyzed the data and talked to also medical partners, and we have found out that the human tends to hold the rollator in such a proximity so that it is relevant to hit its stride length. So with this thing in mind, we wanted to predict also how big the strides of a human, for example, is in order to have an adaptive goal position between the human and the robot. We casted this problem then as a model-based reinforcement learning problem when we want to learn this interaction model of the human and the robot and plan through model predictive control, and from which we were gathering also new data in order to retrain our model with some frequency. And of course, we have warm started these networks through demonstrations with the motion capture data, but in order to be able to cast it into the real world scenario, we leveraged again this hierarchical human-centered tracking, where we are tracking the center of mass of the human, and subsequently we are also tracking with the legs through and extracting the gait parameters through our lasers. And here you can see an ablation study regarding some design decisions in this problem. And I would focus more on the last two parts, the aggregation frequency and the prediction horizon. Here our goal is the minimization of the cumulative cost. So we can see that the aggregation, so how often we are retraining our model, and the prediction horizon, so how far ahead in the future we can predict the human motion, is related to this number 10. So this number 10 is related to the frame rate of the actual laser sensor. And interestingly, this is the mean duration of a stepping motion of the human. So more or less what it says here is that every time a human is completing a step, you want to retrain your interaction model and predict effectively the robotic actions. And here you can see some of the results with the real patient, that we have also compared different strategies, and we can see that basically compared to the actual model predictive control, our results, especially regarding the position and linear velocities, are much better. We also improve the angular velocity, but this is way more challenging to achieve. And I think this is because usually the human tends to turn its torso way faster than its leg while walking. And through the way that we are computing the center of mass, this approach may not be the most effective one to be able to detect something like this. And what we can observe then regarding, for example, why should I learn the model and not do directly model predictive control, is that we see that the model predictive control relies on linearization of the system's dynamics. So this imposes error, and so the usual adaptation is not easy to be achieved. But on the other hand, with the model-based reinforcement learning, we incorporate the advantage of velocity adaptation along with the model-based controller, and this effectively gives us much better control strategies. Of course, I want to say here that all these actions that we are planning are basically proposal actions that we are, of course, moving and applying on the robot. We are not there yet on applying a noisy action policy directly on the robot. So they still need to be smoothed out. So leaving this part, I will take you to the interaction part of the human-robot handover, where we have encoded the engagement of the human to this task as a reward signal for reinforcement learning during collaborative tasks. Here again, we want to track the human. We want a whole pose detection, and I will tell you why in a while. And for this, we have a network of cameras, and we fused basically all the poses and the depth maps that we were collecting. Okay, and here I think you can see an example of the fused reconstructed, let's say, pose, that we don't have any occlusions and we have a very good reconstruction of the pose. Of course, with static cameras, this can be achieved. So from this 3D reconstructed, pose, we have also extracted several features that we have found to be very important for engagement estimation. For example, such features were the gaze direction, the body facing with respect to the robot. And we have inputted this information into a neural network based again on LSTMs in order to be able to classify the engagement of the child to the actions of the robot. And the engagement levels that we were predicting consist between no engagement at all, medium engagement, and maximum engagement. And these three levels of signals that we were predicting were used as a reward in a reinforcement learning settings during child to robot handovers, where the task of the robot was to maximize the engagement of the child into the task with non-verbal activities, so not only motor activities, a task that was particularly important for autistic children to achieve. In the reinforcement learning settings, we use parameterized action spaces, where we have employed a set of discrete actions like walk, look, point, perform a grasp, with some continuous parameters, where through a meta controller we were adjusting these parameters according to the engagement level of the children, till the child would actually go over and hand over the object to the robot. So some of the open problems in this direction, as we said before, in order to learn adaptive robot behaviors, we require efficient measures of interaction. One of the key problems is, can we encode some features that can be used as rewards for human-robot interaction, and can these rewards be sparse, or do we want them to be continuous? How can this affect the performance of the robot? Also, do we need to learn meta-parameters for adjusting, for example, action templates, behavior templates on the robot according to human information, or should we do an end-to-end learning regarding the robot behavior? One of the aspects that we are now actively working on is how we can actively learn safety constraints for human-robot interaction. So it's not only important to have the communication cues and plan the robot actions, but we have to always ensure that we adapt and respect some safety constraints regarding the human motion. And we are studying this in the course of human-robot handovers. And finally, I think it's very important to incorporate multimodality in our robot controllers. And how can we use, for example, multiple cues from different sensors in order to be able to predict the better models that we can use for control? So this concludes also these parts. I don't know if you have questions for this part.
I have a couple quick questions, but maybe I'll save one of them for the end. So what I might have just missed this when you talked about this, but how do you get supervision for the engagement level prediction, like the LSTM that predicts engagement?
You are correct, I didn't say it. So in this work, we were working with psychologists. So it was basically the subjective evaluation of a team of psychologists that would classify the levels of engagement. Because according to research, it's not only these three levels, but we wanted to quantify something in order to be able to use it as a reward signal and be able to quantify the engagement of the child. Yeah.
Makes sense. Thanks.
Yeah. So we leave now the human part and we go to the objects part. So this is basically a line of research that started for me 1 year ago when I came here to TU Darmstadt to study robot learning along with Jan Peters. Basically, one of my key problems that I wanted to study is the interaction with objects and how I can combine these information that I can get so that I can plan later on human assistive tasks. And I started working on 6D pose tracking of objects that are being handled by humans in hard interaction scenarios that basically have a lot of occlusions, and it is an important part if you want to achieve human-robot handover tasks. For the 6D pose tracking, we all know that this problem can be casted as the prediction of the pose of the 6D pose of the object in the next frame. When the classical definition of the pose space is well known, however, we know that it neglects the object's symmetries. And in order to tackle the ambiguity in the rotation representation, we follow some recent research from Brasier et al. That proposes the relaxation of the pose space definition to allow also the description of spherical symmetries. So we leverage this, and I will talk about it a bit more about in the rotation loss that we have used in our 6D tracker. So we have introduced this novel architecture that builds on top of some pre-trained ResNet layers that were pre-trained on ImageNet to bridge the domain gap. And we have introduced in particular foreground and occlusion attention mechanisms. These attention mechanisms, we found out that the parallel architecture was the best choice for us, and it drives basically the tracker in the regions of interest of its frame. Moreover, we have used the FIRE modules and the residual connections, as we have found out that these improve the spatial correspondences of the features. Now, regarding the losses that we have used, we know already that the immediate regression of the pose parameters with the Euclidean loss is suboptimal, as the rotational component lies in the nonlinear SO3 manifold. For that reason, we used a geodesic metric on the SO3, while also employing a 6D continuous rotation representation that was introduced by Tu et al. And allows better learning of the parameters of the rotation parameters. Moreover, since the 3D rotation angle has a different imprint regarding each rotation matrix, we multiply both rotation matrices with an approximate diagonal inertial tensor to assign a different weight to each rotational component. Now, regarding the pose tracking loss, we use a multitask loss that considers the pose tracking loss augmented with auxiliary tasks that refer to the occlusion handling and the foreground extraction. From the advances that we have introduced in this work, I would say that the spatial attention mechanisms for the background clutter and the occlusion handling was one of the advances that we have seen significant improvement in the tracking approach. We have introduced a multitask pose tracking loss that respects the geometry of the object's 3D model and the pose space, and we have achieved the state-of-the-art real-time performance at 40 Hz in hard interaction scenario with a drop of 34% in the translation and 40% in the rotation error. Now we'll talk to you a bit about our current research regarding grasp representations and how we can use these grasp representations to do better grasp planning. So usually the datasets that exist for grasp generation consider many different objects like this, the Jacquard dataset. Let me use also my laser point. So this is the Jacquard dataset, an instance of it. So these bounding boxes is the current representation of annotations for grasping. If for each bounding box, the center represents the exact grasping point in which the robotic hand should be aligned in order to grasp an object. The orientation of this box is the orientation of the hand, and the width of this box considers the opening with which the hand should approach the object to be grasped. Although this kind of representation was very successful in the early 2015-2016, where for example, the RPNs were introduced also in YOLO and so on. However, they have their limitations because they are also considering planar actions. And then Morrison et al. Considered a different approach, leveraging only the depth information of from the camera streams for grasping. However, they had to create the annotations for the depth pixel-wise grasping approaches. For this method, what the authors Morrison et al. Did was actually to propose a grasp map representation that considers a quality map, an angular map defined as a cosine and sinus map, and a width map for the opening of the hand. In order to generate these maps, what the authors did is that they iterated over these bounding boxes by stacking them on top of each other as binary maps. So what they did actually is that they put ones inside every pixel that is inside this box and zeros in all other pixels that are not inside the bounding box. Since this quality map is binary, it is indifferent of the order that the boxes appear in the annotation list, and they basically end up into being overlapped without, and basically being overwritten on top of each other. And crucially, this binary quality map does not ensure that you will find a valid maximum grasp point, since all non-central points in the box are considered an equal grasp point. So the point is that given this representation, although it allowed to do pixel-wise grasp generation, one of the main problems that it has is that even if you take an ideal regressor, you are not able to recreate the annotations. And you can see that if we use the standard intersection over union metric, you can see that the performance declines as you move on to higher thresholds. On the other hand, in our work, what we did is that we created a new representation starting from the point of Morrison et al. In particular, what we introduced here is basically orientation beams. And in each beam, we wanted to preserve the different orientations with which you can grasp an object. We are not discretizing the angles, but we are actually putting them in the different beams of orientation while keeping their real values. For the differences between, for example, of different angles, we have created in particular 3 beams so that we discretize the 180 degrees of antipodal grasps into 3 particular beams, putting inside there the different grasping angles. Moreover, we did not use this binary grasp representation, but we have actually used a soft quality map where we have put ones in the exact position of the grasp point, and while we degraded the values of the points from moving towards the edges of the boxes. With this new representation, we have introduced our new augmented, let's say, grasp representation, where we have the gamma map that represents the graspness, the graspability map, as we say, which contains ones only on the annotated grasp points of the object with respect to the image, and helps us to assess the graspability of the pixel, which is basically the probability of representing a real grasp in the real world. We have the omega maps that represent the gripper, the omega maps that represent, sorry, the width map. We have the Q that are the grasp quality maps, again parsed into the different beams. We have the orientation maps that basically indicate a field angle beam with the respective position. And apart from this grasp representation, we introduced our new architecture called Orange from the orientation attentive robot grasp synthesis that can be used with any particular model, CNN-based model that has the capacity to segment regions of interest and basically boost their performance into being able to produce good grasp representations. And as we can see here, for example, given an input, a depth-based input, initially our quality map, it's a bit greedy. we start by multiplying it with our pixel-wise GraspNet map in order to obtain a graspability refined quality map. And this can actually be seen as a pixel-wise prior regularization, where the graspness acts like a prior probability of a pixel to be a grasping point or not, while the outcome of this multiplication is the posterior that measures the grasping quality. This product is then multiplied by our orientation maps in order to filter out values that result in empty bins for getting our final quality map. The way that we can then compute the maximum grasp center is either as the global maximum over all of the quality map and retrieve the respective values for the angle and the width map. But instead of this greedy approach, in our representation, we can also either employ the different orientation bins to explore best grasps per bin, or even sample, for example, possible grasps through our disentangled representation over the different orientations to provide different grasp positions and orientations. We can see from the results, in particular for the Jacquard dataset, that is one of the most challenging datasets with many overlapping annotations, that when we worked with the GGCNN, that is the network introduced by Morrison et al. That were the first that created this pixel-wise map representation, we boost their performance, while when we use the well-known UNet that has the capacity also to incorporate, to segment better regions, we even got the state-of-the-art performance. Regarding the other works that usually proposed some slight different network architecture, for example, with lighter architectures with more residual connections, we have not applied our orange framework on top of them, but we are confident that this kind of representation, if it's adapted into their approach, can also boost their performance. Finally, we have also made a real robot experiment where we have leveraged our robot here, that is a bimanual robot equipped with a gripper and a 5-finger hand, in order to see how this graph generator performs in a real experiment that is also not a bin picking experiment, because you have to keep in mind that all these representations were used a lot in the standard bin picking experiments that were the main robot grasping problems to be solved in the past 4 or 5 years. For this experiment, we collect the best grasp point across all bins for all the different predicted orientations, and we attempt the ones that are within the feasibility region of its arm in order to showcase the importance of parsing the possible grasp angles. And while with the gripper, we are able to grasp almost all objects. We have a high grasp success. With the robotic hand, the things are a bit different. And of course, this is understandable if we consider that these kind of grasp representations with the bounding box annotations are all considering the antipodal grasps, so grasps that have to be executed by 2-finger grippers. And here is an example, for example, for the chip scan from the YCP dataset, that you can see that even if orange predicts a very good grasp map on the object, and the robot actually reaches for the targeted grasp point, it is unable to lift the robot in the air. And there are different reasons for it, like the morphology of the hand and the low friction between the object and the hand, which result in an unsuccessful grasp, while with the gripper we have way more successes. As a result of this experiment, I think we need to highlight 2 findings. First, the advantage of acquiring the disentanglement of the possible grasp orientation provides a promising framework for planning feasible robot grasps. And I think that a possible future direction here concerns the learning of a policy for selecting the grasp points per orientation. Secondly, and very important, is that a visually good grasp does not mean a successful grasp. It is an indication of a position that may be graspable, but this doesn't mean that it is an actually successful grasp. And I believe here it is very important to combine the effectiveness of algorithms like Orange fused with tactile feedback that can potentially provide a more powerful tool for effective grasping. So regarding this line of research, I want to list again some of the open problems that I identify. So current 6D tracking approaches require synthetic datasets and major data augmentation. And the problem still exists in the scene-to-real gap from the synthetic training datasets to the actual real environment performance. I think it is very important that we should push for model-free tracking methods. I mean methods model-free in the sense that we don't provide an explicit CAD model of the object, since our environments are filled with so many different objects, so it's not easy to generalize there. And I think that we should extend and generalize maybe with better representation, so effectively maybe use the key point, for example, representation as a better way to estimate poses in objects. Another major issue that we are actually currently working on is the multi-object tracking problem, which is still open and challenging since current approaches do not scale well with an increasing number of objects. And I believe that one interesting approach there it will be the combination of self-supervised clustering with hierarchical tracking. Regarding the grasp generation, as we have seen, generalization is very challenging. We are still very constrained with our data sets, and we are constrained also from the way the data sets are annotated. I think that in this line of research, it is very important to connect the grasp proposal generation with the actual grasp plan feasibility, potentially in an unsupervised way, so that we are also able to generalize over different robotic hands and over different robot viewpoints. Because, for example, with the robotic manipulator, the mobile manipulator that we have seen in the previous slide, you cannot have this effective grasping configuration like the bean picking approach, where the camera is installed right on top of the bean, and you can basically perform a pinching action. So this, with respect to the object-related features, I don't know if you have questions for me. Will I go to the last topic of this talk? So.
Sorry, may I?
Yeah.
I already posted in Slack, sorry, in the chat. What's a FIRE module?
A FIRE module. A FIRE module is basically a CNN-based architecture that, if I remember correctly, propagates the signal in a different way. But I can send you the paper that refers to it.
Okay, no, just like because you emphasized that it was necessary,
yeah.
or that you had. Okay.
It actually gave much better results in our ablation studies, but I will send you the paper.
Okay, thanks. Yeah. And my other question is, when you're proposing those grasps, like the gripper that you're using, the hand, it has a force feedback sensor, right? Are you also proposing like a termination signal, like when to like close the gripper until a certain point in time, or until a certain like resistance is met, or is it only about the angle?
So for executing the actual grasp, no, as you are saying right now, we are not following the actual width, although it gives me an indication. We are taking advantage of the actual force feedback in order to understand till which point we should stop closing. That is true.
Okay, thanks.
There was also a question from the YouTube stream from Ping MS. What about the material and the production of the object the robot will try to grasp? As you show in this picture, a hollow can would need less pressure to raise than a full can.
Yeah, sure. I think that this kind of problems should be tackled in combination with tactile sensing. I think that the fusion of, so right now with the visual grasp generation, you just know, as I said, the position in which you want to navigate the hand in order to grasp something. Then we know from our own actions when we are grasping objects that we are adapting our force and the force closure that we apply on the objects with respect to, for example, the weight of the material. I think incorporating tactile feedback and better force signals will be important for better grasp successes in the future. Yeah.
Great, thanks.
Okay, so last chapter in this journey will be about the accelerated manipulation skill learning. And here I will go through two main research directions that leverage demonstration data and then their combination with reinforcement learning and the combination of model-based and model-free reinforcement learning methods. So to start with, we have seen some very big successes by deep reinforcement learning, but however, their unsafe exploration and the prohibitive amount of interactions that they require in order to learn make them hinder their application to real robots. And indeed, like current approaches usually train the robot in the simulation, and then you have to overcome the sim-to-real gap in order to apply the policy into the real robot. Still not quite successful. On the other hand, imitation learning allows the acquisition of control policy when there is not an available accurate world model about the action of the task that we want to solve, and that when there is limited task specification, for example, then there is not a convex objective function that we need to achieve. Moreover, it is an effective way for non-expert robot users to be able to teach, to transfer new skills to robots. In particular, for imitation learning, the use of movement primitives has been very successful for teaching, for example, through demonstration, through kinesthetic teaching new robotic movements. However, this high parameterization of movement primitives for encoding high-dimensional trajectories, like for robotic manipulation, it's very difficult to be optimized and later on with reinforcement learning. So in this in our latest work, what we have done is that we combine movement primitives that provide a distribution of movement parameters and context over the demonstrated trajectories. Context in this case may be the position of an object or the goal position or anything related to the task that we want to solve. For example, in a pouring task, the quantity of the liquid that needs to be poured. And this kind of method can be used in combination with a mixture of principal component analyzers in order to acquire a latent representation over the parameters and the context, while also being able to preserve multimodalities during the demonstrations. The graphical model of this mixture of probabilistic principal component analyzers can be seen as a mixture of Gaussian distributions, which later enable us to represent the multimodalities and the nonlinear dependencies that are inherent in this high-dimensional demonstrated data, while it can also perform denoising, as it can extract the isotropic noise contained in the data. This, I would like to say, yeah, that this kind of denoising is kind of interesting and important also during demonstrations, as, for example, human demonstrations are usually suboptimal, so they have a lot of noise. Moreover, through this probabilistic treatment, we can provide a closed form solution for policy optimization. So with the MPPCA, we can perform policy update in a reduced latent space using off-policy gradient estimations and reusing the samples that were collected in the previous episodes. So we are not only using the demonstrated data from the initial training of the movement primitives, but we are also able to collect new interactions and learn from these new interactions in the environment. Moreover, we are using a forward Kullback-Leibler divergence bound in the trust region optimization, regularization approaches, so that we can restrict the updates of the subsequent policies in order not to forget, so to not go very far away from the safe demonstrated policies. When we are also introducing a KL regularization on the context distribution, so that we don't have like jumps during these changing clusters during the policy optimization, which leads into a robust policy optimization method. And here you can see an obtained policy in a simulation for the problems of reaching a target or closing a drawer that were initially trained through 200 demonstrations and then optimized through our policy optimization approach. And we also use the real robot experiment. For example, here I can show you the pooling task, where initially the robot was trained through demonstrations, through 100 collected demonstrations to learn to pour a specific amount of sugar into this container. However, you can see that this policy obtained through demonstration is not very good. And now we can show how through this policy optimization, while you are keeping this experience buffer and replay, you can actually obtain a much better policy with the poured, the obtained quantity to be very close to the target desired one. And finally, our last work that is an ongoing research, and it's with collaboration with partners from Yale University, from the Grab Lab, considers the model-predictive actor-critic method. This method aims to accelerate model-free reinforcement learning by using approximate MDPs in order to plan and collect guided samples in order to accelerate the learning of actor-critic methods like soft actor-critic, that is the state of the art of model-free reinforcement learning approaches. However, it still needs millions of interactions for achieving the optimal performance. So what we do in this work is that we actually leverage the data that we collect from the real environment in order to learn the dynamics of the environment and the rewards, so that we can approximate the MDP. So by learning the dynamics and the reward, we have this approximate MDP. And for this model learning, we are using probabilistic ensembles that are basically Bayesian neural networks that can learn to capture the aleatoric and epistemic uncertainty in the data. And inspired by model predictive control, we use this approximate MDP in order to plan actions in this MDP and use this data in order to train our soft actor critic. In particular, in this work, we also provide a bound regarding the performance of applying model predictive controller with a learned model. And we show that the performance obtained by model predictive control is basically bounded by the error, the approximation error in the learned dynamics and the approximation error of the value function, which we are actually using in model predictive control in order to be able to plan for longer horizons. So we leverage this approximate MDP to guide the sample in an information theoretic manner. And this particularly means that we do model predictive rollouts with relative entropy exploration. So we try to explore, but in a constrained manner, while acting on the approximate MDP. And actually leveraging the bound that we have provided, and also another bound that was provided by Janner et al. Recently, which basically have proved that acting on the approximate MDP, it's actually as good as acting on the real environment, given some approximation error. So with this case, what we do in our work, we are extending this this model rollout by introducing this information theoretic constraint in the way the model samples will be collected. In this whole framework, the advantages that we have is that we can have efficient model learning through the maximum entropy exploration of soft activity, which in particular then low model learning means better approximate MDP. We can approximate the soft value function that allows also better planning in our model predictive controller. And we are also leveraging the information theoretic rollout for collecting locally good samples, which we then put into a model buffer, we fuse with the real collected data, and then we train our soft activity that actually accelerates the policy learning. And we will see in our results, you can see here the basic antagonist. MOPAC, it's the fastest one in the hub cheetah, while on our learning curves, you can see the accelerated learning in the different Mujoko, OpenAI gym tasks. And in particular, this shows how guiding the task through model predictive control and constrained the way the exploration is being done in the approximate MDP actually helps and accelerates the learning. And with our partners in Yale, we have also applied this method into a robotic hand for in-hand manipulation for 3 different tasks. The first task, it's a common task, I would say, in the model-free reinforcement learning for showcasing the effectiveness of algorithm. That is the valve rotation, where the fingers basically have to push the valve till it reaches a desired orientation. We have solved this quite easily. I mean, the agent learned that it can only use 2 fingers in order to rotate the valve. And then we said, okay, let's make it more challenging. Let's introduce the round valve rotation, where it's like the knob of a door, where the hand has to actually grab the knob and turn it in order to rotate it. That actually we were able to learn it pretty fast. And finally, we also did finger, oops, my presentation lost. I'm sorry for this. There we go. You can see now, yeah. So finger gating means basically grasping, rotate, regrasping, grasping, rotating, regrasping. That was the most challenging task. I don't know if my videos are playing correctly right now, but actually we were able to learn the tasks in 12 epochs, while the MBPO and SAC baselines were actually not quite there yet. So regarding the open problems for this line of research, we can say for sure that having efficient latent representations for policy learning is very, very important. And I think that it's now time to start learning from useful video demonstrations. So we part from this kinesthetic teaching part, and we will be able to learn from visual imitation learning. I think one important aspect is the decomposition of primitives to represent locally linear policies, and eventually build decomposition models or bit hierarchies in order to achieve better task learning. I can argue that even the most complex manipulation tasks can be decomposed into local linear controllers that we can achieve in the end. And also this could allow better transferring or even use local policies in an efficient way, so that we can also explore through these different local controllers. Another interesting research question is whether we can apply some sort of meta controller. So since we can learn, for example, an internal dynamics model, but also learn a policy, can we also learn a meta controller that can decide when we should act by planning in a model-based way, and when should we be more model-free? So this is a very interesting research topic. And finally, I think that one very, very interesting research direction for accelerated skill learning concerns the intrinsic exploration for better model learning. And here, of course, my question is, what are measures of uncertainty? How can we quantify uncertainty, and how can we use uncertainty as a measure for exploration in robotics? And yeah, later on, how can we transfer and generalize over different tasks? Finally, I would like to close up by telling you a bit about the research that I will do in my newly founded group, the IROSA group, where we are going to focus on mobile manipulation. And I think that right now, embodied AI mobile manipulation should be the research that the robotic society should pose for. So problems like robust whole body coordination for mobile manipulation, problems of combining machine learning with planning and classical robotics, effective embodied perception and representation learning, holistic approaches in scenarios where the human is in the loop and you account for the safety, but the interaction with the human is not a separate scenario, but is a part, for example, of a fetch, carry, handover task. And finally, the interleaving of, for example, task and motion planning with learning, so that we will be able to plan multi-stage long horizon goals. Thank you for your attention. And if you have any more questions, I will be happy to answer.
Wow,
Thanks,
incredible breadth. Like, yeah.
Yeah. I know we're running over time, but I guess we could just take a couple questions.
I got some, but since I already asked a bunch of questions, I want to let somebody else go first.
Feel free to send an email or whatever.
Okay. So for the super cool work, and thanks again for showing us. I got a few questions. So for the demonstration, learning, like the imitation learning problem, the way you give the demonstrations to the robot is you set the joints into compliant mode, and then you operate them like manually, or do you like teleoperate?
Yes.
Or like
in this particular work, we do the so-called kinesthetic teaching. So basically, you do gravity compensation, and then you are able to move the robot in the desired positions and etc. Yeah. And I think this is why we should move towards the visual imitation learning approaches.
Gotcha. For the MOPAC, so you showed on the plots that you showed us, we saw the average the average return,
yes.
like on the y-axis against the number of epochs. But I was wondering, what's the wall time? Like, what's the runtime of these algorithms? Like, just intuitively, not like.
So in the simulated examples, each epoch it's 1,000 interactions, while in the real robot environment, each epoch, if I remember correctly, it's like something like 30 interactions. So for the real robot, for the robotic hand task, it requires around 2 hours, I think, if I remember correctly, to solve the most difficult task. While for the simulated task, the timing it's much bigger, mostly because you have to because you want to leverage the model rollout, you want to add as many samples as possible. So this for sure slows down the learning. But the good outcome of this is that you basically protect your robot by not interacting with the real environment so many times as you would have with, for example, applying soft autocritic directly there.
Okay, gotcha. But the time complexity is comparable? Of like, for example, SAC and MOPAC?
MBPO and MOPAC, yes. Between SAC and MOPAC, no. It's way more computationally expensive to run the model-based, model-free approach.
Okay, makes sense, I guess. And last comment that I have is at the very end, you mentioned that you're curious about like using motivation and exploration strategy for like getting into different state spaces. Just a comment here, I would obviously in Montreal we have Marc Belmar and like all of his count-based exploration stuff, so this is really cool. But also at INRIA Bordeaux, my former supervisor is Pierre-Yves Odeyer, and if you check out some of his work,
yes.
oh, okay.
Yes.
Right.
Of course, I am following it.
Okay. Again, thanks so much.
Thank you.
So yeah, I guess like since we're much over time, and also I know it's really late for you, Georgia. It must be past 11.
Yeah.
So yeah, I guess that's like we should break here for questions, but then it is really nice to have you over.
Feel free to email me with any questions, and we'll be happy to have discussions. And yeah.
Yeah. And just as a reminder to most of the others, we take a break next week from the seminar series, and this is because RSS and IROS deadlines are coming up, and also Georgia, if you're submitting to any of those conferences, hope everything goes well. And we really enjoyed having you here, and looking forward to see more work from your group.
Thank you very much. It was very nice talking to you guys.
Thank you so much. Excellent.
Bye-bye.
Ciao.